Hello class, this is Stat 1200. I am your instructor William Buellman, and today we're covering section 3.3, Measures of Position. The objectives for today are to be able to compute and interpret z-scores, to be able to compute the quartiles of a dataset, compute the percentiles of a dataset, compute the 5-number summary for a dataset, understand the effects of outliers, and finally to construct box plots to visualize the 5-number summary and also outliers. The first thing we're going to cover today is z-score. So let's say we had a question and we were wondering who's taller, a man that's 73 inches or a woman that's 68 inches. Well, the answer here is pretty obvious. The 73-inch man is taller because 73 is larger than 68. However, men are taller on average than women are. So now suppose we change the question, we ask, who is taller relative to their gender? Is the 73-inch man taller relative to his gender, or is the 68-inch woman taller relative to her gender? So the way we're going to answer that is we're going to use something called a z-score. So the z-score of an individual data value tells how many standard deviations that value is from the population mean. For example, a value of 1 standard deviation above the mean has a z-score of +1. A value of 2 standard deviations below the mean has a z-score of -2. Let x be a value from a population with mean mu and standard deviation sigma. The z-score for x is z is equal to x minus mu divided by sigma. So that's how we're going to calculate z-scores. It's x, the value that we have, minus mu, the population mean, divided by sigma, the population standard deviation. Here's our first example. So going back to the question I posed earlier, who was taller, the man or the woman? Well, now we're going to use a z-score to figure that out. A National Center for Healthcare Statistics study states that the mean height of adult men in the U.S. is 64.9 inches, with a standard deviation of 3.1 inches. The mean height for a woman is 63.8 inches, with a standard deviation of 2.8 inches. Who is taller relative to their gender? The 73-inch man or the 68-inch woman? We're going to calculate the z-score for each one. The man was 73 inches tall, and the mean for men was 69.4 inches, divided by the standard deviation, which is 3.1 inches, and that gives us a result of 1.16. The height for the woman was 68 inches, the mean for women was 63.8 inches, and their standard deviation was 2.8 inches. So that z-score is 1.5. So since 1.50 is greater than 1.16, we see the woman is taller. Compared to her gender. So here's a note on z-scores. Since the z-score is the number of standard deviations away from the mean, we can easily interpret the z-score for bell-shaped populations. So if you remember before, I said when we had a bell shape, we could use the empirical rule. Well, we can connect that with z-scores now. When a population has a histogram that is approximately bell-shaped, then approximately 68% of the data will have z-scores between -1 and 1. Approximately 95% of the data will have z-scores between -2 and +2. And all or almost all of the data will have z-scores between -3 and +3. We have already learned how to compute the mean and median of a data set as measures of centers. Sometimes it is useful to compute the measures of position other than the center to get a more detailed description of the distribution. Quartiles divide a data set into 4 approximately equal pieces. Every data set has 3 quartiles. The first quartile, denoted Q1, separates the lowest 25% from the highest 75%. The second quartile, denoted Q2, separates the lowest 50% from the highest 50%. Q2 is also the same as the median. Finally, the third quartile, denoted Q3, separates the lowest 75% from the highest 25%. There are several methods for computing quartiles, all of which give similar results. The following procedure is a fairly straightforward method. So we're going to arrange the data in increasing order, as again before with the steps with the median. Let n be the number of values in our data set. To compute the second quartile, simply compute the median, again. For the first or third quartiles, proceed as follows. For the first quartile, compute L, which is equal to 0.25 times n. For the third quartile, compute L, which is equal to 0.75 times n. If L is a whole number, the quartile is the average of the number in the position L and the number in position L plus 1. So L gives you position, just remember that. If L is not a whole number, round it up to the next whole number. The quartile is the number in that position corresponding to the rounded up value. So that's the second thing you have to remember about quartiles. There's 2 things. L is the position, not the number. And second, if it's not a whole number, you need to round up always. Here's example 2. The following table presents the annual rainfall in inches in Los Angeles during the month of February over several years. Compute the quartiles for the data. So the data we have was already arranged in increasing order. That's good. There were 45 values. For the first quartile, we're going to compute L, which is equal to 0.25 times 45, which gives us 11.25. Since 11.25 is not a whole number, we round it up to the next whole number, which is 12. The first quartile is the number that is in the 12th position. So if we look back at our data set, Q1 is going to be the number in the 12th position, which is 0.92. For the second quartile, we compute the median using the methods previously presented. Again, the middle number. The median here, Q2, is equal to 3.12. And finally, for the third quartile, we have to compute that L again, which is 0.75 times 45, which gives us 33.75. Since 33.75 is not a whole number, we have to round it up to the next whole number, which is 34. The third quartile is the number in the 34th position, which is Q3, which is equal to 4.94. So again, these L's that we're finding are giving us the position, and then we go look back in the data set and count to that position, and that's the number. So now suppose we just didn't want to split the data set into 4 chunks like we did with quartiles. So we have something else. Quartiles describe the shape of the distribution by dividing it into fourths. Sometimes it's useful to divide a data set into a greater number of pieces to get a more detailed description of the data. Percentiles divide the data into hundredths. For a number p between 1 and 99, the percentile separates the lowest p from the highest, 100 minus p. So, for instance, the 90th percentile separates the lowest 90 from the highest 100 minus 90, which is 10. So it separates the lowest 90% from the highest 10%. Like I said, it's similar to quartiles, but instead of just breaking the data into 4 pieces, we're breaking it now into 100 pieces. The following is the procedure for computing the pth percentile of a dataset. The first step for computing percentiles is to arrange the dataset in increasing order. Just like quartiles and just like the median, we need them in increasing order. Let n be the number of values in the dataset. For the pth percentile, we compute L by doing p divided by 100 times n. If L is a whole number, the pth percentile is the average number between L and L plus 1, just like quartiles. And if it's not a whole number, we round up to the next whole number, again, just like quartiles. Here's our third example. The following table presents the annual rainfall in inches in Los Angeles during the month of February over several years. So this is the same data set as before, but this time we want to compute the 60th percentile for the data set. Again, the data set's already in increasing order. There's 45 values. So to find the 60th percentile, we have to calculate L, which in this case is equal to 60 over 100 times 45, which is equal to 27. Since 27 is a whole number, the 60th percentile is the average between the 27th position and the 28th position. Thus, we see the 60th percentile is 3.57, the number in the 27th position, plus 3.71, the number in the 28th position, divided by 2, since we're taking the average, which is equal to 3.64. So here we have that the 60th percentile is 3.64, and 60% of the data is below that number, and 40% of the data is above that number. So another thing we can do with percentiles is sometimes we're given a value from a data set. So we're just given a number, and we wish to compute the corresponding percentile for that value. Here's the procedure to do that. Again, arrange the data in increasing order. Let x be the value whose percentile is to be computed. So x be the value of the percentile we're trying to compute. Use the following formula. The percentile is equal to the number of values less than x plus 0.5 divided by the number of values in the data set. When you get this, round the result to the nearest whole number. This is the percentile, the corresponding value. Notice here we just round to the nearest whole number, not round up, round to the nearest whole number. So you got to remember all these rules. Example 4, again, we're going to use that Los Angeles rainfall data. And the year that we're going to try and figure out is when it rained 1.90 inches, and we want to know which percentile that corresponds to. Again, the data is already in increasing order. There's 45 observations. If we count, there are 17 values less than 1.90. So our percentile, remember, is 100 times the number of values less than x plus 0.5 divided by the total number of values in the data set. So it's going to be equal to 100 times the number of values less than x in the data set, which was 17, plus 0.5 divided by the number of values in the data set, which was 45. When we calculate this, we get 38.9, which when we round is 39. So 1.90 corresponds to the 39th percentile. The 5-number summary of a data set consists of the median, the first quartile, and the third quartile, the smallest value and the largest value. These values are generally arranged in order. The 5-number summary of data set contains the following quantities. So we list the minimum, Q1, which is the first quartile, Q2, which is the second quartile, which remember is equal to the median, Q3, which is the third quartile, and the maximum. So that's the 5-number summary, and typically we're just going to list it like this. So we'd put the minimum, comma, Q1, comma, Q2, comma, Q3, comma, the maximum. So that's how we would write the 5-number summary. Example 5, we're back to our Los Angeles data set for rainfall. So we already know that Q1 is 0.92. We know the median is 3.12 and Q3 was 4.94. The minimum of the data set we can see is right here, which is 0.00. The maximum of the data set we can see is right here, which is 13.68. So our 5-number summary is going to be the minimum 0.00, comma Q1, which is 0.92, comma the median, which is 3.12, comma Q3, which is 4.94, comma the maximum, which is 13.68. So that is our 5-number summary for this Los Angeles rainfall data set. The next topic we're going to talk about are outliers. An outlier is a value that is considerably large or considerably small compared to most of the data set values. Some outliers result from errors. For example, a misplaced decimal point may be the cause of it to create a much larger or much smaller number. Some outliers are indeed correct. They simply just reflect some anomaly in the data set that's really extreme. Here's example 6. The temperature in a downtown location is measured for 8 consecutive days during the summer. The readings in Fahrenheit are 81.2, 85.6, 89.3, 91.0, 83.2, 8.45, 79.5, and 87.8. Which reading is an outlier? Is the outlier an error, or is it possible that it's correct? So we have to think about the context here. This is summer, and we know temperatures are somewhat related, so they should be fairly close to each other, and there shouldn't be all of a sudden an extreme gap. So here we have 83 and 79, but in between them we have 8.45. That is very cold when compared to 83 and 79.5. So we're going to say that 8.45 is an outlier, because it has an extreme value when compared to the rest of the data set. Now, if we look at it, is it possible that 8.45 is actually a legitimate temperature in the summer? No, it's not. That is below freezing, an error. So when we're trying to detect outliers, one of the tools we can use is called the interquartile range. The interquartile range is found by subtracting the value of the first quartile from the value of the third quartile. So here you see IQR is equal to Q3 minus Q1. The most frequent method used to detect outliers in a dataset is the IQR method. In order to use it, we have to do the following. First, we have to find Q1 and Q3. Then we compute the IQR, which is Q3 minus Q1. Compute the outlier boundaries. These boundaries are the cutoff points for outliers. The lower outlier boundary is Q1 minus 1.5 times IQR. And the upper outlier boundary is Q3 plus 1.5 times IQR. Any data value that is less than the lower outlier boundary or greater than the upper outlier boundary is considered to be an outlier. Example 7. The following table presents the number of students absent in a middle school in northwestern Montana for each school day in January. Identify any outliers. So here's all the values right here. You can see them. Suppose that we used technology and we got that the Q1 was 45 and Q3 was 59. So first we need to compute the interquartile range, which was Q3 minus Q1, which is 59 minus 45, which is equal to 14. So now that we have the IQR, we can calculate both the lower outlier boundary and the upper outlier boundary. So the lower outlier boundary, which was Q1, which in this case is 45, minus 1.5 times our IQR, which is 14, which gives us 24. And our upper outlier boundary, which is Q3, which was 59, plus 1.5 times 14, which gives us 80. There are no values less than the lower outlier boundary of 24. The value 100, however, is greater than the upper outlier boundary, therefore 100 is an outlier. A box plot is a graph that presents the 5-number summary along with some additional information about the dataset. There are several different kinds of box plots. The one we used here is called a modified box plot. Here's example 8, which uses the absentee data from the middle school in Montana. Remember that the quartiles were Q1 equals 45, the median, which is Q2, equals 51, and Q3 equals 59. So in order to draw the box plot, we're going to have to draw vertical lines at those points. But first, let's get a scale going. So let's do that down here. So here's 40, 50, 60, 70, 80, here's 90, and here's 100, here's 110. So we're going to draw vertical lines at those points. Here's 45, here's 51, and here's 59. And then we're going to connect them together, just like that, to make the box of our box plot. Now we're going to calculate the upper and lower outlier boundaries, which are going to be the whiskers of our box plot. So first, to calculate the lower outlier boundary, it's Q1 minus 1.5 times the IQR, which remember, again, was 24 from before. And the upper outlier boundary is Q3 plus 1.5 times the IQR, which remember was 80 from before. The largest value in the data set that is less than the upper outlier boundary is 77. So we draw a horizontal line to that point. Even though the upper outlier boundary is 80, we don't draw it all the way to 80. We draw it to the largest value that is less than or equal to the upper outlier boundary. Upper whisker done, we have to do the lowest whisker. The smallest value in the data set that is greater than the lower boundary is 41. So 41 is the smallest value in the data set that is greater than or equal to 24. So we draw the horizontal line on the lower side from 45 to 41. So those are the whiskers of our box plot. Finally, to complete our modified box plot, we have our box, we have our whiskers. Now we need to put any outliers, which we have the one outlier which was at 100, so we're going to put an X right here. And now we have a complete box and whisker graph or a modified box plot with outliers. And you notice at the bottom here, I've now labeled it. Now that we're done, this is the number of absences. So this is a graph, so we want to have a label. Here's a box plot, and here's some shapes of the data we can get from these box plots. If the median is closer to the first quartile than the third quartile, or the upper whisker is longer than the lower whisker, the data is said to be skewed to the right. So here's data right here. We remember, we see it, the bulge right here, and then it tails off to the right, so that's skewed to the right. And below it right here is roughly what the box plot for a skewed to the right data set may look like. If the median is closer to the third quartile than the first quartile, or the lower whisker is longer than the upper whisker, the data is skewed to the left. So remember, we have the bulge of the data here. It tails off to the left, so that's skewed to the left. And below it here is a sample of what the box plot could look like. If the median is approximately halfway between the first and the third quartiles, and the two whiskers are approximately equal, the data is approximately symmetric. So remember, if we have kind of this bell shape-ish, we have that it's approximately symmetric, and here is what a sample box plot would look like.